5.3, connecting f prime and f double prime with the graph of f. Here we have a graph of f. On the left side, we have the absolute minimum. Right here we have a slope of a tangent line that is 0, but no extrema on this, no extreme values. The derivative goes from being positive to positive. So even though the slope here is 0, there's no extreme value. Up here we have a local maximum. Here we have a local minimum, and over here we have an absolute maximum where f is actually, f prime is undefined. We have no extrema here. The derivative goes from being negative to being negative across this 0. And then finally, on the endpoint, we have a local minimum. Theorem 4, first derivative test for local extrema. The following test applies to a continuous function f of x. At a critical point C, 1, if f prime changes signs from positive to negative, then f has a local maximum value at C. If the derivative changes from positive to negative, that means the function increased and then it decreased, creating this local maximum. And the same even if the derivative is undefined. If your values go, the slope of the tangent values go from positive to negative, you must have a maximum value there, at least a local maximum. If f prime changes signs from negative to positive, then you have a local minimum. If the values go from negative to positive, that means the function decreased and then increased. That creates a minimum value. If f prime does not change signs at C, then there is no local extrema. This one, the derivatives go from positive to positive across this 0, so there's no extreme values here. At a left endpoint A, if f prime is less than 0 for x greater than a, then f has a local maximum or minimum value at a. So you can have a local max at an endpoint, and you can have a local minimum at an endpoint as well. At a right endpoint B, if f prime is less than 0 for x less than b, then f has a local minimum. So you can have minimum values at endpoints as well. Just like I said, well, in the last slide, I guess I used minimum and maximum. Well, I guess they did too. Example 1, using the first derivative test. For each of the following functions, use the first derivative test to find the local extreme values. Identify any absolute extrema. Let's take the derivative of this function, f prime of x equals 3x squared minus 12, and we'll set that equal to 0. We want to know where this function levels out, and then we'll see if the derivative changes signs across these zeros. Let's factor out a 3. We get x squared minus 4. 0 equals 3 times x plus 2, x minus 2. So we have some possible extreme values at positive and negative 2. Let's throw those on a number line. We have negative 2 and 2 as possible mins or maxes. Then we test values around these values. So negative 3, 0, and 3. And we're going to plug these values into the derivative. We're testing the derivative to see if the function increases or decreases in between these values. When we plug negative 3 in, we get 3 times 9 minus 4, which is a positive times a positive. So that's positive. This function is increasing to negative 2. And actually, instead of writing a plus, we have some symbols that will make your life a lot easier down the road. And what I write when the derivative is positive is I say, well, this function is increasing to negative 2. Then in between negative 2 and 2, if we plug 0 into the derivative, we get 3 times negative 4. This function decreases in between negative 2 and 2. Then when we plug 3 in, we get 3 times 9 minus 4 is positive. So really a positive times a positive. This function then increases after 2. There's a local max of something at x equals negative 2, and we have a local minimum of some y value at x equals 2. Now there's a local maximum at 2 because this function increases the 2 and then decreases. Then there's a local minimum because this function decreases from -2 to 2, and then after increases. Now we have to find those y values. Let's plug -2 into the original. When we plug into the original, we get -8 plus 24 minus 5. We get 16 minus 5. We get a value of 11. Now let's plug 2 in. We get 8 minus 24 minus 5. That's -16 minus 5. That's -21. Go ahead and pause if you didn't get all this written down. Go ahead and write it down. Looks like I used the space under B, so I am going to erase this. So now that I can do letter B. Letter B, let's find g prime of x. That's equal to first times derivative of the second plus the second times the derivative of the first. I can factor out, well, let's do this. Let's go, I can factor out an e to the x. And we get x squared minus 3 plus 2x. We get e to the x. If I rearrange these, I would have plus 3 and x minus 1. So we have two possible places of extreme values, -3 and 1. So those have potential to be minimums or maximums. Let's put those on a number line. We have -3, 1 as potential candidates. And we'll test -4, we'll test 0, and we'll test 2. Now we're going to plug these into the derivative. This is a nice place to plug it into, because then we can just get positives and negatives. E to the -4th, e to the anything is going to be positive, so we have a positive times -4 plus 3 is negative, and -4 minus 1 is negative. So this function is increasing to -3. E to the 0 is 1, it's positive, and then we have times a positive times a negative. This function decreases from -3 to 1. Then at 2, let's plug 2 in. E squared is positive, 2 plus 3 is positive, and 2 minus 1 is positive. This function increases after 1. We have a local max at x equals, actually, we need the of, maximum of something at x equals -3, and we have a local minimum of something at x equals 1. Now let's plug -3 back into the original so we can get the y value. Let's see, we're plugging in -3. That's 9 minus 3 times e to the -3. That's 6 over e to the 3rd, whatever that is. 6 over e to the 3rd. Then let's plug 1 in. We get 1 minus 3 times e, so we get -2e. -2e. Definition, concavity. The graph of a differentiable function y equals f of x is concave up on open interval I if y prime is increasing on I. So concave up looks like that, and concave down looks like this. The concavity test. The graph of a twice differentiable function y equals f of x is concave up on any interval where the second derivative is positive. So the graph opens up if the second derivative is positive, and the graph opens down if the second derivative is negative. That would be concave down. Determining concavity. Use the concavity test to determine the concavity of the given functions on the given intervals. Y equals x squared on 3 to 10. Used to determine concavity. The first derivative of x squared is 2x. The second derivative is 2, which is always positive. So this graph, I don't care if it's on 3 to 10 or 5 to 7 or -12 to 100, this graph is always concave up. Well, think about what this is. It's a parabola that opens up. So no matter where you are, this graph is concave up. It really doesn't matter in this case that it's from 3 to 10. For B, the first derivative is the cosine of x, and second derivative is negative sine of x. And we're looking at from 0 to 2 pi. So let's see, where is sine 0? Sine is, because graphs can change concavity where the second derivative is 0. So we want to know where negative sine of x is equal to 0. Well, we want to know where sine of x is equal to 0. Sine of x is 0 at 0 and, 2 pi. Actually, we have pi also, don't we? So x equals 0, pi, and 2 pi. So let's plug those on a number line. We don't want to be outside of 0. We're going to test in between 0 and pi, and then in between 0 and 2 pi. And we don't want to include these because it's an open interval, but we'll check pi. Well, we can check anything from 0 to pi, so how about pi over 2? And how about 3 pi over 2? Now we're testing this in the derivative, and the derivative is negative, actually right here, negative sine of x. We're testing this in the second derivative because we're testing for concavity. The sine of pi over 2 is a positive 1, so the graph is concave up. And then the sine of 3 pi over 2 is negative 1, so it's negative. The sine of pi over 2 is 1, but we have a negative 1. So we have negative sine of pi over 2, which is negative positive 1, which is negative 1. So it's the second derivative is negative between 0 and pi. 3 pi over 2, we have negative sine of 3 pi over 2. Now remember, we're testing the second derivative. That's negative negative 1. So this graph is concave up from pi to pi over 2. So we say concave down from 0 to pi. Actually, concave down on 0 to pi, and concave up on pi to 2 pi. Points of inflection. The curve y equals 3 plus sine x in example 2 changes concavity at the point pi 3. We call pi 3 a point of inflection of the curve. Now the concavity changed over pi. The concavity went from being concave down right here to concave up after pi. So at one point it went from being concave down to concave up. Right there. We call that a point of inflection. Definition, point of inflection, a point where the graph of a function has a tangent line. So that's the first thing. It has to have a tangent line there. In other words, the first derivative has to exist where we have points of inflection and where the concavity changes. So the concavity has to change. That's a point of inflection. We have y equals 3 plus sine of x, and at pi, there's a point of inflection right here, and then we have y2 is sine of x. That has a point of inflection right at the same spot. Finding points of inflection. Find all points of inflection of the graph of y equals e to the negative x squared. The first derivative is e to the negative x squared times negative 2x. So let's rewrite that as negative 2x e to the negative x squared. The second derivative is first times derivative of the second times negative 2x plus the second times the derivative of the first, which is negative 2. Now this is equal to 4x squared e to the negative x squared plus e to the negative x squared. Actually, we should write it like this, I suppose. Minus 2e to the negative x squared. Well, we can factor an e to the negative x squared out of this and get 4x squared minus 2. The zeros of the second derivative indicate where we have possible points of inflection, only possibilities. We have 4x squared minus 2 is, we want to know where that's equal to 0. So 4x squared equals 2. X squared equals 1/2. So x equals plus or minus the square root of 1/2. Now those are possible points of inflection. We'll throw these on a number line, negative 1 over square root of 2 and 1 over square root of 2. 1 over the square root of 2 is 1 over something bigger than 1, so it's not even 1. So we're pretty safe to plug in negative 1, 0, and 1. Let's plug negative 1 into the second derivative and decide if the concavity changes. So if we plug negative 1 into the second derivative, e to anything is positive. So we have a positive times 4 times negative 1 squared, that's 4 minus 2, that's positive. So this function is concave up here. When I plug 0 in, either the 0 is 1, in other words positive, times a negative 2, which is negative. So between negative 1 over square root of 2 and 1 over square root of 2, it's concave down, so we have a point of inflection. Let's plug 1 in. E to anything is positive, and then 4 minus 2 is positive, so concave up. Both of these points are points of inflection. Now it said find all points of inflection. So we have points of inflection at, we have negative 1 square root of 2, comma, and so if we plug that into the original function, we have e to the negative 1 over square root of 2 squared, e to the negative 1/2, so 1 over square root of e. So this one is 1 over square root of e, and we have another one, and we have a positive 1 over square root of 2, comma. Let's plug positive 1 over square root of 2. E to the, this is plugging it into the original, negative 1 over square root of 2 squared. E to the negative 1/2, so 1 over square root of e. 1 over square root of e. Example 4, reading the graph of the derivative. The graph of the derivative of a function f on the interval negative 4 to 4 is shown in figure 5.25. Example 4, reading the graph of the derivative. The graph of the derivative of a function f on the interval negative 4 to 4, closed interval, is shown in figure 5.25. Answer the following questions about f, justifying each answer with information obtained from the graph of f prime. So letter A says, on what intervals is f increasing? Remember, this is the graph of f prime, not the graph of the original function. We know that a function is increasing when its first derivative is positive. The first derivative is positive from negative 4 to negative 2. So negative 4 to negative 2. And also from negative 2 to 1. Now how do we know that? How do we know that the f is increasing? We know that f prime is greater than 0. It's positive. B, on what intervals is the graph of f concave up? We know that the graph, the original function, is concave up when the second derivative is positive. So we're looking for slopes of tangent lines that are positive to this graph, because the second derivative is the slope of the tangent lines to the first derivative. So we see that from negative 2 to approximately 0, the slopes of the tangent lines are all positive. Then that doesn't happen again until we get to 3. Now the slopes of these tangent lines are all positive. So we know that the original function is concave up from negative 2 to 0 and also 3 to 4. And does it look like 4 is at 0? Yeah, it does. So I will not include, no. I can include it because we're looking at slopes of tangent lines. So 3 to 4. Now how do I know that? How do I know that the intervals, these are the intervals where the graph is concave up? I know that slopes of tangent lines to f prime are positive or greater than 0. C, at which x coordinates does f have local extrema? So where is the local extrema for the original function? We know that there's possibilities when the first derivative is 0, but then the first derivative has to change signs over those zeros. So the potentials are -2, 1, and 4. Well, we have extreme values where the first derivative changes signs. Now the first derivative across -2 goes from positive to positive, so there's no local extrema there. But then at 1, the first derivative goes from positive to negative. So we have a local extrema at x equals 1, and we also have a local extrema at x equals 4 because that's an endpoint. Now how do I know on what intervals is a graph at one x coordinates does f have local extrema? F prime changes from positive to negative over 1, and 4 is an endpoint. Letter D, what are the x-coordinates of all inflection points of the graph of f? Well, that's where the second derivative changes signs. And the second derivative on this graph is the slope of the tangent lines. So we're looking at where the slope of the tangent lines are changing signs. So I have slopes of negative here, and then across 2, I have positive. So there's a point of inflection at 2, D. Point or points of inflection at x equals -2. We have a point of inflection at 0 because the slopes change signs over approximately 0. It's a little to the left, but we'll say at x equals 0. And then there's another point of inflection at 3 because the slopes go from negative to positive. And of course, the slopes are 0 at each of these, but that's not good enough. Just having a slope of 0 is the potentials. Then the slopes actually have to change signs over those values. So x equals -2, 0, x equals 3. Now how do I know that? Slopes of tangent lines to f prime change signs. Sketch a possible graph of f on the interval -4 to 4. Well, let's sketch it on this same set of axes. Now I know that over here at -4, my graph actually, the original graph increases because the derivative is positive. So since this is increasing right away, let's start down here. And this graph increases until we get to -2. And not only does it increase, the slopes are negative, so it increases concave down. So you could go concave down, but you could have a function increasing and be concave up, but we don't want that. We want the function to increase and be concave down. So increase, concave down, right there, to 2. Then this function goes from being concave down to concave up, but still increases. So that's where you get your point inflection. Now this function is going to increase. It's going to change concavity at 0. So it will increase to 0, but then change concavity and keep increasing until you get to 1. So there's a point of inflection, and it'll be concave down and increase till it gets to 1. Then this function decreases until it gets to 4. So then finally it decreases, concave down until we get to 3. So here it'll start to decrease, concave down, but then when it gets to 3, it's concave up but still decreasing, and it doesn't necessarily have to hit that same point, but that's how I drew it. Studying motion along a line. A particle is moving along the x-axis with position function x of t. Find the velocity and acceleration and describe the motion of the particle. So we have velocity is equal to 6t squared minus 28t plus 22. The acceleration is equal to 12t minus 28. Now to describe the motion, we're going to say when this moves to the left, when does it move to the right, when is it stopped, when is it speeding up, and when is it slowing down. So we have all that information that we have to find out. Let's let's see if we can factor this. I can take out a 2, 3t squared minus 14t plus 11. We have 3t and t. And let's see, I have minus 11 here and minus 1. So we have t equals 11 thirds, t equals 1. That's where the function is, or that's where the particle is stopped. So we can say t equals 11 thirds, t equals 1. Now let's put those values on a number line. We have 1 here, and we have 11 thirds here. Let's look at going right and left. Maybe we test 0. 11 thirds is 3 and 2/3. So 2 and then 4. Let's plug 0 into the derivative. We have 0 minus 11, that's negative, and 0 minus 1 is negative. So this function is increasing or going to the right from negative infinity to 1. Actually from, oh, wait a minute, we're at t greater than or equal to 0. So I have to be careful. I probably don't want to test 0. Let's test, instead of 0, let's test 1/2 just to make sure that we're getting correct values. If I have 3 times 1/4, that's certainly going to be smaller than negative 11, or smaller than 11. So negative times, and then 1/2 minus 1 is negative. So this is still, I find out that this function is increasing from 0 to 1. Now the particle is going to the right from 0 to 1. It's okay to test 2. I have 6 minus 11 is negative, but then 2 minus 1 is positive. This function now is going to the left, or the particle is going to the left. We have 12 minus 11 is positive, and 4 minus 1 is positive. Then this function increases, or the particle goes to the right. So left is from 1 to 11 thirds, and to the right is from, we found out 0 actually has a positive value, 0 to 1, and then union with 11 thirds to infinity. Now let's look at whether this speed, when it speeds up, when it slows down. We do that by setting the acceleration equal to 0. 12t minus 28 is equal to 0. 12t equals 28. T is equal to, let's see, if I divide them by 2, I get 14 over 6. I get 7 thirds, which is 2 and 1/3. So 2 and 1/3 is about right there. Well, now we have to test some points here. How about to the left of 7 thirds? I could test 2 again. 2 into the second derivative is 24 minus 28. So we have negative acceleration. And then to the right of 7 thirds, we could use 4. And we'd have 48 minus 28. That is positive. So here we have a positive acceleration. So this function from 0 to 1, has a positive velocity and a negative acceleration. So from 0 to 1, this one is slowing down. From 1 to 7 thirds, we have a negative velocity and a negative acceleration. So from 1 to 7 thirds, this one is speeding up. Then from 7/3 to 11/3, from 7/3 to 11/3, we have a negative velocity and we have a positive acceleration. So from here to here, now we're slowing down. They're opposite. And then finally, from 11/3 to infinity, we have a positive acceleration and a positive velocity. So from here to infinity, we are speeding up. So speeding up, that's from 1 to 7/3. So 1 to 7/3, union with, I think there's another one, and then 11/3 to infinity. Now, velocity and acceleration were opposite, or slowing down, from 0 to 1. And is there any other place slowing down? Yeah, 7/3 to 11/3. So 7/3 to 11/3. Second derivative test for local extrema. Instead of looking for sign changes in y prime at critical points, we can sometimes use the following test to determine the presence of local extrema. If you have a derivative that is equal to 0, the first derivative, but at that first derivative, the second derivative is negative. All right, let's look at that. Let's say this is the original function right here. And you have a first derivative that is 0, but you have a graph that is concave down. That means you have a local maximum there. Then if the first derivative is 0 and the second derivative is positive, the original graph could look like this. The first derivative here is 0. That means there's a potential min or max. Then if your second derivative is positive at this point, that means it's concave up and you have a local minimum. Example 7, using second derivative test. Find the local extreme values of this function. So the first derivative is 3x squared minus 12. I can factor a 3 out of that. We can factor this into x minus 2, x plus 2. Of course, we're setting this equal to 0. So x equals 2, x equals negative 2. Well, we could throw this on a number line, or we could just do the second derivative test. We could say, well, the second derivative is 6x. Now, if you evaluate this at x equals 2, we find out that's 12, and so it's concave up. If we evaluate this at x equals negative 2, we get negative 12, so it's concave down. At 2, if it's concave up, then we have concave up. It is a minimum. Minimum. And if it's concave down at this value, then we must have a local maximum.